All right, let's get started here. So if I'm right, you just turned in a homework assignment, the first part of Chapter 12, and then the second half of Chapter 12 is due on Tuesday, the 2nd of April. So there's a little bit of a gap there, isn't there? Because we're only on the 14th of March, so you've actually got a little bit of time till your next homework assignment. Of course, there's also a big vacation in between. But the next thing that's up is the design project, and that's on Tuesday of next week. By a show of hands, have you already installed water gems? Who has water gems operational? So there's a couple of people who haven't yet got water gems installed on their machines. I really think you need to do that as soon as possible. The design of the pipes and the optimization you're going to have to go through, it doesn't take hours and hours, but you can't do it until the software is installed. So get on that as quick as you can, and if you have questions along the way, then feel free to stop by to see me. Also, looking a little bit further into the future, you've got Exam 2, and that's going to be on Thursday the 4th, and so that's the Thursday after we get back from spring break. The coverage for that exam includes lectures 14, which is the next lecture after the first midterm, through 21. And so that's going to include the class meeting that we have right before the exam. So any questions about the announcements? How do I make this go away and never come back? Maybe like that? Oh, that's better anyway. All right, well, we're going to continue talking about discharge depth applications, and so that's an extension of specific energy. Remember, specific energy is when we're measuring the amount of energy relative to the channel bottom. And so what we're going to be looking at today is when the channel bottom isn't regular, like when there's a drop down or a step up, and how that affects the specific energy. And at the extreme, when you have interruptions in the channel like that, what it can do is it can choke the flow. And by choking, what we mean is that there's some sort of an obstruction there that's causing the water to pool upstream. And we'll talk about why the water pools when we put an obstruction. Sometimes it pools, sometimes it doesn't. So we'll get into all of that today, and here's the corresponding section from the book. Now, previously, this was kind of the big idea in terms of the graphical representation of specific energy. And the question that we'd looked at was, if you have a certain flow rate, and we have a whole variety of different slopes that we can use to send this flow through some sort of a channel. And so I think the specific numbers that we used in class previously was for a flow rate of 10 cubic meters per second and a channel width of 4 meters. What's all the many different combinations of depth that there can be? And you know, if we have it be really shallow depth, then to get 10 cubic meters per second through there, the velocity has to be high. Or if we have a deep depth, then the velocity would be low to have the same 10 cubic meters per second. And so the specific energy diagram comes to a point. Do you remember what we call this location where there's the minimum specific energy? What's special about that spot at the far left edge of the figure? It's critical. Yeah, that's right. It's critical. And so the minimum specific energy corresponds to the critical depth. And the critical depth is the depth at which there's the most hydraulic efficiency. So just to reiterate, what we were doing in this figure is we were using a variety of different depths to find out how much specific energy there is. And what we were assuming is that the channel width was staying constant, the roughness of the material was the same, and it was all for the same flow rate. I pointed out that if the critical depth is here, the far left edge of the specific energy diagram, then we can use this diagram to tell us for a given depth whether conditions are subcritical or supercritical. So in this figure, it looks like the critical depth is around 0.86 meters. So what if the flow depth that we're actually observing is 1 meter. Are conditions critical, subcritical, or supercritical if the actual observed flow depth is greater than the critical depth? That's right. It's sub. And so the reason that's the case is that if the observed flow rate is deeper than critical, that means you have a relatively slow-moving velocity, and it's those slow-moving velocities that cause subcritical flow. And so supercritical flow is when you have a very fast-moving velocity. And so the fast-moving velocity would be corresponding to a depth that's less than the critical depth. All right, so that's just a brief review of what we were talking about last time. Now, another kind of figure that's important to look at is a discharge depth diagram. So this is a little bit different because what we're doing is we're having the specific energy stay constant, whereas this figure had a lot of different specific energies. What we're saying is if there's just a certain amount of specific energy, let's find out how much flow rate we can get with that amount of energy. So you can think sometimes of energy as currency. You know, energy is what's available to do the work, in the same way that you can put your money to work to do tasks, to buy food. You know, it's something that you can spend. Well, energy is also available to do something. And here what we're saying is for a constant amount of energy, let's investigate a whole variety of different flow rates that there could be. And so here on the horizontal axis is a certain flow rate, and then on the vertical axis is the depth that's associated with that. So what this figure is showing is that for a certain amount of energy, you could have a really shallow depth, and that shallow depth wouldn't have as much flow rate as this special point where we're maximizing the flow rate, and it just so happens that that point of maximal flow rate corresponds to the critical depth. And of course that's not a coincidence, because what we talked about last time was that the critical depth is a location of maximum efficiency. It's the point at which we can accommodate the most flow for a certain amount of energy that's available. And so one way to think about critical flow is it's the minimum amount of specific energy for a certain discharge. That's what we looked at last time. That's what this figure had to say about critical depth. Critical depth was the minimum amount of specific energy for a certain fixed Q. But the other way of looking at it is if you have a certain amount of energy available, then you can maximize discharge when the flow is at critical conditions. So critical flow corresponds to the maximum discharge for a certain specific energy. E, overall, includes two terms. Remember that specific energy is a little bit different from total energy. We went into this in class last time. What are the two terms of specific energy E? Consists of what two terms? The depth, so y, and then v squared divided by 2g, so velocity head. So depth and velocity head. Good. What is another way of expressing the velocity head instead of v squared divided by 2g? Good, good, good. Q squared divided by 2g a squared. Now, we use this term in terms of q squared divided by 2g a squared, when we don't know the velocity, but we may want to be solving for y. So we sometimes use this when solving for y. Because y, if it's an unknown, then it's just more convenient to have that unknown directly expressed rather than velocity, and then it's kind of like a secondary thing that the velocity would be dependent on the depth. So this gets at the depth more directly, and you'll see that in two of the examples we worked today. So discharge depth is just saying that if you've got a certain amount of energy, you can have a whole variety of depths. You could have a shallow depth and a high velocity. You could have a deep depth and a low velocity. And all of those different combinations can give you the same amount of specific energy, but they won't necessarily result in the same flow rate. All right, so now consider the following. Let's say that water is flowing along. I'm going to bring the shades down a little bit because it seems to cast a bit of a glare. Water's flowing through a channel, and conditions here are going to be non-uniform. What's the first clue that flow is going to be non-uniform? Yeah, the depth is changing. There's a step downward. And so if there's a step downward like this, then that means that the flow conditions are not constant with respect to position. Now, you'll notice that here in the sketch, what the author has done has put in a little imaginary dashed line to indicate what the critical depth should be for that channel. There was a little shortcut method that I showed you for calculating the critical depth if it's a rectangular channel. You know, last time in class I told you you can find y sub c. If it's a rectangular channel, then you can calculate the flow per unit width, lowercase q squared, divided by g to the 1/3 power. So let's say that, you know, if this is a rectangular channel, they've done that. They've calculated the critical depth, and here is the critical depth. But the observed depth, what we actually see, is greater than the critical depth. So what's the flow regime at location 1? Subcritical. Right. I'm going to keep asking that to just kind of reinforce your ability to see if conditions are sub, super, or critical. So here, at location 1, conditions are subcritical. That's another clue that we get from the sketch here. We have a non-uniformity in flow, and it's subcritical upstream of the step down. You can also see that what they're saying is that it's going to be subcritical downstream. And that's one of the first lessons to draw from this, is that the upstream conditions oftentimes are going to govern what happens downstream. And so here, since it was subcritical upstream, it's going to be subcritical downstream. And we have to know that because you're going to be solving a cubic equation. And when you solve the cubic equation, it's going to give you 3 roots, which suggest 3 depth alternatives. One of them will be a negative depth, which we can throw out. There's no such thing as a negative depth. And then the other 2 alternatives correspond to the alternate depths. One alternate depth that's supercritical flow, and another alternate depth that's subcritical flow. So when you solve that cubic equation, you're going to look at this and you're going to say, well, since it was subcritical upstream, it's going to be subcritical downstream. And then that'll tell you which of the remaining 2 roots to select. All right, so this is a step down, a bed drop. And the classic problem type that's associated with this is what will be the new depth downstream. It's not going to be the same depth. And the reason why is that the flow is gaining energy between 1 and 2. Think about how much energy is there at 1. Well, we could say that right now at 1, the specific energy is however much the depth is and the velocity head. But at 2, there is that same amount of energy there was at 1 plus the amount of energy that was gained by the water dropping down that step. And so falling down that step, it's gaining specific energy. Now, either we can diagnose the flow conditions at 1 by comparing the actual flow depth to the critical depth. That's one way to diagnose the flow regime. The other is to look at the Froude number. Remember, any Froude number greater than 1 is supercritical conditions. Froude number less than 1 is subcritical conditions. Here is the specific energy diagram, and this graphical approach explains why it's going to be deeper at location 2. If we took a ruler and we measured on that figure, hopefully the author made a scaled drawing. You can't always count on that, but their scaled drawing should show that the depth has increased between location 1 and location 2. And this figure explains why. What this figure says is, let's start with y1, because that's what we know is this depth here at 1. So identify that initial depth on the specific energy diagram. So that's this. Now, I'm really proud of this animation. Do you see that colored arrow that's just popped up on screen there? You're looking at 45 minutes of effort to get these arrow lengths right, and so that's just the kind of guy I am. So we start here with depth 1, we go over to the specific energy diagram, intercept, and then go down to E1. So that's how much energy you have before the step. Now this is really important. We shift to the right along the specific energy diagram horizontal axis. So from E1 to E2, you can see that the delta Z, you're gaining specific energy because you're dropping down. Just think of gaining energy, like you're going on a log ride and you go off the edge of the cliff or whatever. So you've gained energy, and the corresponding depths with this new specific energy at 2, there are 2 crossover points on the specific energy diagram. So we go straight up again, and we're crossing the energy curve at the supercritical depth and the subcritical depth. And since we had subcritical at 1, of these 2 alternative depths, we choose the subcritical choice. And then that's when we go back over to the vertical axis and we identify the new depth at 2. So a problem like this can be solved graphically if you take the time to put in a whole variety of possible depths and create a specific energy diagram. It's not hard to create a specific energy diagram. You saw the table in class on Tuesday that you'd need to create one. You just put in a bunch of possible depths, a bunch of corresponding velocities and so on for a certain flow rate. But we can also solve it without using the spreadsheet. We can solve directly by setting up a cubic equation and solving for the roots. And so that's what we're going to do in this example. We've got a rectangular channel with a width of 8 feet. And we want to know if there is a 1.2 foot bed drop. If the delta Z is 1.2 feet, then what will be the new depth downstream at 2? So let me summarize on the whiteboard here what you need to, the steps you need to take to solve this problem. And then we'll go through them together after I give you some time to consider it. So the first thing is diagnose the flow regime at 1. So flow regime at 1. What are the 2 ways we can tell if flow at 1 is supercritical or subcritical? Don't just go by the drawing. You actually have to analyze. Okay, either the Froude number or flow depth versus the critical depth. Either one of those will tell you super versus sub. So when I say flow regime at 1, we're trying to find out, is it supercritical or sub? That's the question. All right, so once you know that, then the next thing to do is find out what is the specific energy at 1. So it's just simply going to be related to y1 plus v1 squared divided by 2g. Or if you choose, you could say q squared divided by 2ga squared. So that's E1. And then step 3, E2 is going to be E1 plus delta Z. So find out what is the E2, and then we'll go through the rest of those stages together. All right, so the three steps I said we should take a look at is, first of all, classify the flow regime at location 1. Because we're going to need to know whether it's subcritical or supercritical in order to choose the correct route at the very end of the problem. So the two ways we can do that, diagnose the flow regime, is number one, we can calculate the Froude number. And if we take that approach, then the Froude number is going to be for this rectangular channel where we're carrying 30 cubic feet per second, so Q squared times T. T is the top width, which will just be 8 feet. Here for the traditional units, G is 32.2 feet per second squared, and then the cross-sectional area is 8 feet times 3.5 feet, so 28 feet squared. And it's really easy to lose track of the thing that you're supposed to cube that area. So don't forget to cube the area before you take the square root of everything. So the Froude number is less than 1, which means flow conditions are subcritical. Just as an alternate check of that, on the whiteboard here, I've written down the formula for a rectangular critical depth. It's the lowercase q, flow per unit width, squared divided by g, all to the 1/3 power. So from that, we could calculate that the critical depth is 0.759 feet. And since 0.759 is less than the stated flow depth of 3.5 feet, then that's another indicator confirming flow conditions at 1 are subcritical. Okay, so is everybody with me so far about flow conditions are subcritical at 1? We feel good about that? So then the next thing to do is use this equation, which defines specific energy, and find out how much specific energy is there at location 1 before it goes through that drop. Just as an intermediate step, because I know I'm going to need it, I calculated the velocity of flow at 1. So Q divided by the cross-sectional area at 1 gives me the velocity. And so the amount of specific energy that there is at location 1 is the depth and the velocity head. The depth is 3.5. The velocity head works out to be 0.0178 feet. So together, that's 3.5178 feet of energy at location 1. And so then at location 2, it's going to be that same amount of specific energy plus the drop down of 1.2 feet. So E2 is 4.718 feet. So what we do now is we rewrite the energy at 2 in terms of the unknown flow depth. So let me erase this top bit off of the whiteboard. And what we know is E2 is 4.718 feet. And E2 is defined as Y2 plus Q squared divided by 2GA squared, right? And by Q squared divided by 2GA squared, we can substitute that a little bit further. What we can say is that that is the Q in this problem, 30 cubic feet per second, so 30 CFS squared divided by 2 times 32.2 feet per second squared, so 2GA squared. Now A is just the width of 8 feet minus the depth at location 2, and then we have to square the area term. So Q squared divided by 2GA squared. So what you'll see is that we have an equation and there's only one unknown. The only unknown is the depth at 2. Okay, so set that up as a cubic equation and find the roots. What we ultimately want to know is what are the 3 roots to this equation. One of them will be negative, then one of them will be subcritical, one will be supercritical, and that'll allow us to know what's the new depth downstream. All right. Here what I've done on the screen is a little bit different from the whiteboard. On the screen I combined here's E1, here's E2, and then the step of 1.2 feet. But what we knew is that the overall amount of specific energy at 2 is 4.718 feet, and that's equal to the depth and the velocity head. And when we're expressing the velocity head in terms of the unknown depth y2, then the factor is going to be 0.2184, and that's just where we have 30 cubed and divide it by 2g times 8 squared. So all of that combined together is just this number coefficient up in the numerator, 0.2184, and then y squared in the denominator. And if we multiply all three of these terms by y2 squared, then the cubic equation you can see is y2 cubed minus 4.718 y2 squared plus 0.2184. So there are going to be three solutions to that cubic equation. And just like Manning's equation for a trapezoidal channel, solving cubic roots is something you have to maybe refresh on the Casio, because it's going to be critical over the coming lectures. You'll find yourself solving these cubic equations over and over and over again. So maybe it's been a while since you had to do that, but it's important. And what we'll find is that the three roots is, here's a negative root, a subcritical root where the depth is shallow. I'm sorry, supercritical depth is shallow, and then the subcritical root where the depth is greater than the critical. And so in our case, here's the answer, 4.708. So this is the new depth at 2. So after that step down, the flow's gaining some energy. And as a result, it's going to set itself up at a new flow depth. This is just when you've got a certain amount of specific energy, there are two options for what the flow depth can be, a supercritical option and a subcritical option. When you've got that much flow and a certain amount of energy to convey it. So those are really the two governing things in this channel is, number one, what is the Q? And number two, what is the E? And we want to find out the flow depth for that combination of flow rate and specific energy. Any questions about this example? So this was a step down. What if there's a step up? Similar things happen. Instead of gaining specific energy, you're losing specific energy. In the case of a step down, there isn't the risk that the flow will become choked. You're not going to start pooling the water and causing it to get deeper and deeper upstream. But in the case of a step up, that is a risk, depending on how high the delta Z is. So let's say this is a relatively small delta Z. That's the first case we're going to consider. So same as before, there's a certain amount of specific energy at 1, and the specific energy is the depth and the velocity head. Now in this case, what they're saying is, let's measure the total energy relative to the channel bottom at 1. So here they're labeling this line TEL, that means total energy line. And what they're saying is that from location 1, which is upstream, to location 2, downstream, the amount of total energy doesn't change, even if the specific energy is changing. So you can think of the amount of energy at 1 as how much energy there is to push the water up over this obstacle. That step up is an obstacle, and E1 is the energy available to overcome it. The specific energy, instead of increasing, at location 2 there's going to be less specific energy. So E2 is however much energy there was at 1 minus the delta Z. In the previous case, it was plus delta Z, because we were going down over a drop-off. This time, specific energy is being removed. but the total energy doesn't, because we're just gaining some delta Z. Remember, the difference between total energy and specific energy is just in the case of specific energy, you're ignoring the elevation below the channel. But in total energy, you are considering some delta Z above a datum. Okay, now let's consider this from the specific energy diagram, SED, specific energy diagram. So before we went through and there were the arrows that told us how to find the new depth. We can follow the same approach here. We'll start with our known depth at 1, and we'll go sideways and intercept the specific energy diagram, and we go down. And this is how much energy there is at 1. And instead of going to the right, like we did last time, since this is a step up and that decreases our energy, we have to shift to the left. So you see that the delta Z is moving, the E2 is further to the left on the specific energy diagram than E1 was. That means there's less energy at 2. And so there's 2 possible depths that the flow can be at for this amount of energy. The flow can either be at a supercritical depth or a subcritical depth, and since it was, in this case, subcritical to begin with, then it'll be subcritical after the step, and so this is how we would graphically identify the new flow depth at 2. And from a quantitative perspective, it's the same as what we just did on the whiteboard here, except for that the delta Z is added to the other side of the equation. Okay? So here, the new depth is going to be shallower than the depth at 1. Y2 isn't going to be as deep as it was upstream because of that removing specific energy. What if conditions were supercritical before the step up? So look here, we have the critical energy depth has been calculated, and here's the observed depth. In this illustration, the observed depth is less than the critical depth, and so that means we've got supercritical flow conditions. And so if you have to go up over an obstacle, we can follow the same procedure of starting with Y1, going over to the right, intersecting the curve, and going down to find out the E1. So the intersection with the energy axis is E1, and then we lose specific energy. So here's the delta Z, and going back up, that means that the depth at 2 is going to be deeper. So if you have an obstacle, what that forces the water to do is get deeper if the conditions are supercritical at the upstream location. All right, well, let's practice, number 1, doing things like classifying the flow regime. Let's practice finding either the Froude number or the critical depth. Let's practice solving cubic roots. This is very similar to the last one, except that this time E2 equals E1 minus delta Z. So here we're saying that the amount of energy at 2 is less than there was energy at 1 because of the step up. So the step up in this case is 0.5 feet. Got a flow of 250 CFS. So it's basically the same procedure as we did before. We want to find the new flow depth, Y2. On the whiteboard, I showed you the Froude number. The Froude number is 0.394. Since it's less than 1, that means it's subcritical conditions at 1. If we look at it according to critical depth versus the observed depth, the critical depth is 2.69 feet. And since the observed depth in the problem, it says that at location 1 it's 5. Since the observed depth is greater than the critical, then that means that's another confirmation that you've got subcritical flow. So you don't necessarily have to always do both of these, like Froude number and a depth comparison. Either one is sufficient for classifying the flow regime upstream. So with that knowledge that it's subcritical at 1, we now find the amount of specific energy there is at 1. So it's the depth and the velocity head. So there's 5.388 feet of energy at 1. And then at 2, we have to subtract out the 0.5 feet of energy. So the energy at 2 is going to be 4.88 feet. And then that energy at 2 is distributed between the depth and the velocity head. And I guess here what I've had with this 9.705, that's q squared divided by 2ga squared. And a for this rectangular channel is going to be 10 times y. So if you square that, in the numerator of this velocity head term, you've got q squared. In the denominator, you've got 2g, and then the width of 10 squared. So in any case, when you rearrange that as a cubic equation, we get this, and the 3 roots are the negative root, which we immediately reject, and then we can choose between the supercritical and the subcritical alternative, and we choose the subcritical because it was subcritical upstream. It'll stay subcritical. So what this step caused is that the depth is going to go from the initial depth was 5 feet, and now it's decreasing in depth. And that is what we would expect according to that same process that we went through here, that if you were in the subcritical range, a step up causes the depth to decrease. So our calculations match what we'd expect from the specific energy diagram. Okay, any questions from that example? All right. Remember that you can calculate the Froude number, and if the Froude number is equal to 1, that means critical conditions. So this formula, where we have some top width and the depth is at critical conditions, we could use this formula to find out the depth of critical flow for any type of geometry, trapezoidal, rectangular, triangular, quarter circle, half circle, whatever. But if you've got rectangular flow geometry only, is when this would be applicable. One of the interesting things is that when you have a rectangular channel, the water depth is 2/3 of the specific energy that's present. And that sometimes can be a little bit of a time saver if you know that of the energy that's there, the depth is 2/3 of it. That's we'll remember that and use it in class on Tuesday. But just as a check of that, let's say that we had 50 cubic meters per second going through a 5-meter wide rectangular channel. And so for critical conditions, what's the specific energy there? So let me just show you in the calculations here what I mean by that. So if we have 50 cubic meters per second and the channel is 5 meters wide and it's rectangular. Okay, lowercase q is flow per unit width. So flow per width. 50 cubic meters per second going through 10 meters of width means that for every 1 meter in the channel width, we've got 10 cubic meters per second going through there. Now that's just an average, because in the center of the channel, in reality, there would be more flow going through that center meter than through an edge meter. But we neglect those edge effects here when we're calculating the flow per unit width. So what this is saying is you can calculate the specific, the critical depth by saying the flow per unit width squared divided by g. So the critical depth is 2.168 meters. Now, What I told you is that the critical flow is 2/3 of the specific energy. So Y sub C is 2/3 of E. Another way of saying that is that E is 3/2 of YC. So if you have critical flow conditions and you know the critical depth, you can find the specific energy just by multiplying it by 1.5. And that's what this next part is saying is 3/2 of the critical depth means that the specific energy is 3.252. Now this approach only works if it's a rectangular channel. But let's just double check and see if that's actually the case. And so here the velocity in this illustration, if you had a flow depth of 2.168, so if it was the critical depth, then the velocity you'd be seeing is 4.613 meters per second. And so here's the depth and the elevation head. And so the elevation head is 1.084, and it's proving this shortcut that it's 2/3 of the specific energy exists as the critical depth under that specialized condition. Now, why does it matter? We're going to look really in depth about chokes on Tuesday. Like, if you keep putting more and more obstructions in a channel, like piling up logs, eventually the water isn't going to have enough energy to make it up over that obstruction. There's some critical height of how tall that obstruction can be. And just at the precipice of starting to choke the flow, like when you've just barely put so many obstructions in the channel that it's going to begin to pool upstream, then the water conditions will flow at the critical depth over those obstructions. And then the calculations we do are a little bit easier if we can just say, well, the specific energy that's present is 3/2 of the critical depth. It saves us from having to solve for the velocity head. So that's why I wanted to mention this shortcut idea that the water depth is 2/3 of the specific energy that's present. So what equation is used to find the new downstream depth? The specific energy equation. All right. Now this is what I was talking about with beginning to choke the flow. We'll just step through this progression of ideas and then leave it there for today. So this is showing that initially we have subcritical flow upstream, and what it causes, the depth will decrease downstream. Because remember, there's less energy available because we had to use up some of the specific energy to get over that obstacle, delta Z. So what if delta Z gets a little bit bigger? So here in step B, what this is saying is that the delta ZB is larger than the first delta Z was. And so what does that do to the depth at 2? The depth gets even shallower because now there's less energy than there was before. And so you'll notice that the velocity head is going to be a little bit larger than in the first case. Now, if we keep increasing the step height so that now we're causing the critical depth at the downstream location, that's as far as we can go. There's no more efficient depth than the critical depth. So now we've kind of maximized the height of the step that's allowable. And if we make the delta Z any bigger, then there won't be enough energy to push the water over the obstacle. Earlier today, what I told you is think of E1 as how much energy there is to push the water up over the obstacle, but you still need to have some energy left over, not just to get over the obstacle, but also to carry the flow through the channel. And the most efficient way to carry flow through the channel is at the critical depth. That's how you get the biggest Q for the least amount of E. That's how we started the lecture, was looking at that idea. So what I'm saying is there is some delta z, some obstruction distance, where if we're trying to step up over a greater obstacle height than that, we won't have enough energy at 1 to do it. And then it would start to choke the flow. Now this diagram is really complicated, but what it's showing is E1 is how much energy there was before we overdid it with the step up. If we make this delta z d, so condition D is just like a really big step, a step that's larger than the maximum allowable step to prevent pooling. We can call that like the critical step height. Condition C here, where it's saying delta z c, it's a critical step height because any more additional height and there won't be enough energy to get over it. So let's say we go beyond that boundary. I mean, physically it's possible to make the step a little higher. So if we do, what has to happen is that the water depth upstream needs to get deeper so that there's enough energy to overcome the obstacle. So for a few minutes, we have unsteady flow. And unsteady flow means that the water depth is increasing upstream until it gets to y prime 1. So you'll notice y1 was the original depth upstream. Y prime 1 means it's the depth the water is going to have to pool to so that there's enough energy at 1 to make it over this new obstruction. So E prime 1 is the amount of energy required to make it over this obstruction, delta Z sub D. We're going to pick back up with this same idea when we gather on Tuesday of next week. So before I let you go, let's take a look at these announcements. The first is that on Tuesday you're going to upload 2 maps. One of the maps is showing me your system performance under the design flow rate. The other map is showing me your system performance under static conditions, meaning no flow. The annotations that are required, I showed you that in class last time. Remember, it's where you're putting labels for the junctions, the flow demand at each junction, length and diameter of each pipe, pressure at each junction, identifying the elevation of the reservoir location that you've selected. So if you have any questions about what needs to be annotated, the thing to do would be go back and look at that slide that was in class on Tuesday. Any questions before we finish for today? All right, I'll see you on Tuesday.